Hi all, let's take a look at the Achieve homework assignment for section 8.2. The first three problems of this assignment, there's really no work to be shown in them. It's just watching a video that they have along with using some of their tools from Desmos to answer questions about arc length. So I want to start with question 4 with you, the first one that we actually have to do some work in. They're wanting us to find the arc length of two linear functions. The first one is 5x plus 4. We're supposed to find the arc length from 0 to 6. Okay, so I know the arc length formula is going to be the integral from where the region begins to where it ends of the square root of 1 plus the first derivative squared. So that's exactly what I've done. I've taken the first derivative, found that it's 5, and so then I said the arc length is the integral from 0 to 6 of the square root of 1 plus 5 squared. Of course, that's the square root of 26. When you integrate the square root of 26, and remember, the variable is understood to be times x to the 0. When you integrate that by the power rule, you get the square root of 26 times x to the first. And now we said, well, we're just evaluating that from 0 to 6. So of course we're going to get 6 on the root of 26 for our final answer. When you evaluate it at 0, you get nothing. Similarly, for the second one here, they give me the arc length, or ask me to find the arc length on the curve 4 minus 5x from 1 to 6. Okay, so yet again, my derivative is just the coefficient of x. It's going to be negative 5 this time. And so the arc length is going to go from 1 to 6 of the square root of 1 plus a negative 5 squared. But just like last time, it doesn't matter if that's a 5 or a negative 5. Since you're squaring it, that's a 25. 25 plus 1 is 26. We have the square root of 26 in there. When you integrate that, you get the square root of 26x. The difference is this time now is we're evaluating from 1 to 6. When we evaluate it at 6, you get 6 on the root of 26, just like the last problem. But then I'll have, for the lower limit, we subtract off 1 on the root of 26. Well, 6 on the root of 26 minus 1 on the root of 26 gives me my answer of 5 on the root of 26 for that final solution. Now, this next one requires a little bit more work, so let me go full screen here with you. So the function that they gave me in this one was y is equal to 1/4 x squared minus 1/2 the natural log of x, and I was asked to find the arc length from 1 to 6e. Okay, so I take the derivative. I take this derivative carefully. The first term, I'll get 1/2 x to the first, and then please remember the derivative of the natural log of x is 1 over x. So the derivative of minus 1/2 is just going to be minus 1/2 natural log of x, I'll say is 1 over 2x. 1 over 2 times 1 over x is 1 over 2x. Now, I'll go ahead. I know I need to square out this first derivative. And please remember, whenever you square two terms, you're going to get 4 terms. And in this case, the middle 2 terms combine to be minus 1/2. It's 1/2 x times a negative 1/2 x to the negative 1, and then you'd have another one for your inside. If you have any trouble seeing where these 3 terms comes from, what you need to do is you need to rewrite this 2-term expression times itself, FOIL it out. I promise you'll come to these 3 terms here. Now, that's the square of the derivative. And then I can say, well, all right, but I need inside that square root, I'm going to have 1 plus the square of the derivative. So I can see all that's going to do is it's going to change that minus 1/2 to a plus 1/2 in the middle. And then just as this was a perfect square trinomial because it was equal to the group 1/2 x minus 1 over 2x quantity squared, this trinomial is also a perfect square expression, where I can say, well, the first term is just going to be the first term of this is the square root of this term, which is x over 2. The last term is the square root of this term, which is going to be 1 over 2x. And then in order to obtain that plus 1/2 in the middle, I need a plus here. And then keep in mind that middle term is going to come from x over 1 over 2x times 1 over 2 times x plus times 1 over 2 times x to the negative 1. That x and the x to the negative 1 cancel out of that middle term. And then I would have another one, but that one would give me 1/4. I would have another 1/4 to gain a total of 1/2. I didn't want to bother showing the algebra since this is a calculus class, but please make sure you don't let an algebra mistake mess you up on these problems. You've got to be able to get to this in this problem, because if you can't get to that, you can't work the integration. So now I'll say, okay, once I get to this, how do I integrate? Well, the arc length, it's going to be the integral from where the region ends to where it begins, 1 to 6e, of the square root of this expression, 1 plus the first derivative squared. Now, like I said, we had to get that as a group squared, because now that group squared and the square root counteract one another. And you say, well, they just cancel, and you'll have what's inside of that square root. And now we know that we can evaluate this by the power rule. We'll just get 1 over 4x squared, and then this term, remember, the integral of x to the negative 1 is the natural log of x. So you'll get plus 1/2 natural log of the absolute value of x. Really don't need the absolute value in this problem because my limits of integration are all positive. And then whenever you evaluate at the limits, when I evaluated it at 6e, I would have got 36e squared over 4. That's where the 9e squared comes from. And then plus 1/2 natural log of 6e. When I evaluate at the lower limit 1, I just get minus the lower limit, which is going to be 1/4, and I know that the natural log of 1 is 0, so I just get the minus 1/4. Now on achieved, they wanted a decimal place answer to 3 decimal places, so you'll see I put the 67.647, and that's what they wanted there. For the next question here, it goes back to an easy one. I'm not quite sure why they did number 5, a gorgeous problem, and then number 6, backtracking to an easy question. It's just a linear function again. So you have y is equal to 8 minus 9x, and we're supposed to find the arc length between 1 and 3. So as always, you need to take the derivative. Now, derivative is just negative 9. Then the arc length formula is the integral from where it begins to where it ends, 1 to 3, of the square root of 1 plus the first derivative squared. We know when we square a negative 9, we get 81. That's going to be 81 plus 1 for a square root of 82 in there. When you integrate that, you'll get the square root of 82 times x. Now we're evaluating that from 1 to 3. So we'll get 3 on the root of 82 minus 1 on the root of 82. For my final answer here that you can see I got of 2 on the root of 82. And that is precisely what they were wanting. Now, we're switching to surface area for the last 3 problems, and it's really not that big of a change. You just say, well, the surface area, it's the same formula as the arc length formula, the difference being that we have to take into consideration the rotation. That's the 2 pi r, where r is just your function's value. So it's 2 pi f of x on the square root of 1 plus the first derivative squared dx. So now if I just have the function x, as is in this problem, and I want to find the surface area of the revolution about the x-axis of y equals x from 0 to 3, then I can say, all right, 2 pi r becomes 2 pi f of x, 2 pi, and then f of x is just my x. Please remember, any function of x must be put inside the integral. You have to deal with the integral of that. Any constant can easily be factored to the outside. So we have 2 pi on the integral from 0 to 3 of x, and then the square root of 1 plus the first derivative. Well, and I didn't even write it, but you can see the first derivative here would be 1. So 1 squared, still 1. You're going to have the square root of 1 plus 1 on the inside, which is the square root of 2. You bring that square root of 2 to the outside and say, well, that's going to make it 2 on the root of 2 times pi. But then when you integrate the inside, you'd have x squared over 2. It's going to cancel that 2 out, but remember, I still have the root of 2 as well, so I'll have pi on the root of 2 times x squared evaluated from 0 to 3. Plug in the 3 and you'll get a 9. So we have 9 on the root of 2 times pi, or you could say 9 pi on the root of 2. And then, of course, minus 0 for the lower limit doesn't change anything. So I know what you're thinking. You're thinking, that problem was just a little too straightforward. I definitely would agree with that statement. The next two get more fun, but not bad. Number 8, it asks us to find the arc length of the cubic function 2x cubed from 0 to 1. All right, so, and they're wanting an exact answer on this one. So I took my 2x cubed and I said, well, I know I'm going to have to take the derivative and square it for my formula. So the derivative was 6x to the second. If I square that, I get 36x to the fourth. Surface area formula, 2 pi on the integral from where it begins to where it ends, 0 to 1, of f of x, 2x cubed, on the square root of 1 plus the first derivative squared, 1 plus 36x to the fourth, integrated with respect to x. Now, as soon as I saw that I had an x to the fourth on the inside and an x to the third on the outside, I knew substitution was going to be an easy solution to this problem. So notice that's what I did here. I said, let's let u equal the inside, the 1 plus 36x to the fourth, and then du, I can say, well, the derivative of 36x to the fourth is going to be 4 times 36, 144, x to the third with respect to x. Now, from this step to this step, what I did is I didn't want to bother going in through and showing I need to multiply by 144 on the inside. And in fact, I only needed to multiply by 72 on the inside. I already had a 2x cubed dx, but I need a 144th, so that's an additional factor of 72. So I would need to multiply the inside by 72, which means I divided the outside by 72. Well, please notice from this step to this step, 2 pi divided by 72 reduces down to pi over 36 here. So that's what happened with the 72 that I had to force in and go to the outside. Now the rest of it, we know all of that's going to cancel out and become du. The rest of it's just the square root of u, which is just u to the 1/2 du. Once I get that taken care of, I take care of the limits of integration. So I can say, well, my lower limit was 0. Now that lower limit, if you evaluate u at 0, you'll get the 1. My upper limit was 1. Well, 1 plus 36, now your upper limit is 37. So we're integrating from 1 to 37, where my function that I'm integrating is u to the 1/2. Integrating that by the power rule gives me u to the 3 over 2 times 2/3. I went ahead and simplified and said, well, 2/3 times pi over 36, that would give me 2 pi over 108, which reduces down to pi over 54. And then I'll say, well, it's going to be pi over 54 times what? Times u to the 3 over 2 evaluated from 1 to 37. It's going to be 37 to the 3 over 2 power minus 1 to the 3 over 2 power, which is just 1. And I just left my final answer in that form since they wanted an exact answer as opposed to a decimal approximation. And you can see that that was precisely what Achieve wanted in this instance. Now, the last problem here for this extremely short section, for number 9, it's at least a fun problem, kind of reminiscent of the arc length problem number 5. So whenever I go in and try to work it, I have 1/4 x squared minus 1/2 natural log of x. And I'm trying to find the surface area from revolving this curve about the x-axis, starting at x equals 6 and ending at 4e. All right, so I take the derivative. Derivative is going to be 1 over 2 times x, and then I would have minus 1 over 2 x to the negative 1. Similar to number 5, I could have called that 1 over 2x. This time I thought it would be easier if I just call that x to the negative 1. Now when I square that out, you square the first term, you square the last term. The middle term is always going to be 2 times the first term times the second term. So you say, well, the first term times the second term, that's going to be 1/4 x to the 0. It's just 1/4. Now, and it's a negative 1/4. I should say, since that term times that term would be negative. Now you have to multiply that by 2 to get your minus 1/2. Of course, if you want to write that expression by itself and FOIL it out to get to this, you're welcome to do that. Now, I know that this is the first derivative squared. 1 plus the first derivative squared is just going to change out that middle term to a positive 1/2. And then this is just like I was saying before, it is absolutely critical that you understand that this 3-term expression can be written as a binomial squared. In the same manner that when I said the first derivative squared gives me this 3-term expression, well, now when I work backwards, it's just that original first derivative with a plus sign in between if I have a plus 1/2 in the middle. Now, it's important to get this because when I go to my problem and I can say, well, it's going to be 2 pi on the integral of f of x, which is your original function, on the square root of 1 plus the first derivative squared, I need to write that 1 plus the first derivative squared as this entire 2-term expression squared. That way the square root and the square cancel, and I can say, well, I'm just going to have my f of x times this 2-term expression all integrated with respect to x. Absolutely. What do you do after this step? Well, you always have to do any algebra before you do the calculus. So what I've done from here to here is I've just FOILed out on the inside. I said 1/4 x squared times 1/2 x is 1/8 x cubed. 1/4 x squared times 1/2 x to the negative 1 gives me a plus 1/8 x to the first. My next term, I would get minus 1/4 x ln x, and then I would have, again, minus 1/4 natural log of x. This time it'd be divided by x, or times x to the negative 1. I thought it looked better to put it in the denominator. Now, all of this is inside of an integral, of course, still evaluated from 6 to 4e. Now, as soon as I saw this, I looked at it and saw, well, the first 2 terms, they're going to be easy to integrate. The 3rd term and the 4th term, they're not going to be hard to integrate. This one will require integration by parts, and the last one will require substitution, since if I let u equal the natural log of x, du will be 1/x dx. So I can say, okay, if I wanted to go ahead and separate the first 2 out here front, I noticed that they both had coefficients of 1/8. So I went ahead and factored out that 1/8, and that gave me the pi/4 out in front. And then inside my integral is just x cubed plus x integrated with respect to x. Then I separated this next term. I can say, well, my next term is just going to be that right there. What do I want to do with that? Well, I'm going to factor out that minus 1/4. 2 pi divided by 4 went down to pi/2. And again, remember, it was minus pi/2 on this same integrand. But now on the inside, I'll have x ln x, and I'll integrate that with respect to x. Lastly here, again, this term had a coefficient of negative 1/4. I brought that out, multiplied it by the 2 pi to get minus pi/2 times the integral. And now I have my natural log of x over x. Now, I knew that this one was just power rule. This one and this one required some more work. So I showed that additional work in red. I said this is going to be integral A down here, and this will be integral B over here. So integral A, if I just wanted to think about what is the integral of x ln x dx without worrying about the definite integral on it to begin with, I could just say, well, I know that there's a natural log in there. Normally when that's the case, it's going to be integration by parts. I let u equal the natural log of x. Derivative of that is 1/x dx. dv is anything else in there, which is the x dx. When you integrate x with respect to x, you'll get your 1/2 x squared. So now integration by parts formula tells me that this integral is going to equal u times v, positive 1/2 x squared natural log of x, and then minus the integral of v du, minus the integral of v du becomes minus 1/2 x squared times 1/x just gives me the integral of x dx. I know that's ridiculously easy to integrate. It's just going to be x squared over 2. So I have my 1/2 x squared natural log of x minus 1/2, and then this integrated to my x squared over 2, or 1/2 x squared. Now I stopped there, and I didn't put a plus c because I know that this is going to go back inside of a definite integral when I work the problem. Similarly, with this last part that I labeled integral b, I showed its work over here. If I wanted to integrate the natural log of x over x, true integration by parts, if you have a natural log, is normally the option. But remember, integration by parts also, you want to have a product in there. As soon as you have a quotient, you should be thinking substitution, and substitution works gorgeously, and it's really easy on this one. U is the natural log of x, du is 1 over x dx. So I can say, well, then the 1 over x dx all becomes du. Then the natural log of x is the only thing left in there, and you know that that's u. The integral of u with respect to u is going to be u squared over 2. When you back substitute, u is just your natural log of x, quantity squared over 2 now. So then I go back into my surface area formula, and I can say then this surface area is pi over 4. And in this first group, I used the power rule to get my x to the 4th over 4 plus x squared over 2, evaluated from 6 to 4e. And then I said, okay, this next one is going to be the integral for a. I already had a minus pi over 2 out in front, but then I noticed both terms in the answer I had for the integral of the expression a had a 1/2 in them. So I went ahead and factored that out, and I said, well, that's going to be pi over 2 times 1/2. I got another minus pi over 4 out in front. And then when that's out in front, you'll get your x squared natural log of x minus 1/2 x squared left over inside of there, evaluated at the same 6 to 4e. And then especially since those two already had a pi over 4, I thought, well, wouldn't it be nice if this one was pi over 4? Well, it really is. The reason is because you had minus pi over 2 times whatever this integrated to, which was the natural log of x quantity squared over 2. So I factored that 2 out of the denominator, multiplied this 2 in the denominator to give me my pi over 4. And then I just have my natural log of x quantity squared evaluated from 6 to 4e. So then the only thing I did, especially when I saw that everything was being multiplied by pi over 4, is I just said, well, I can factor out a pi over 4, and then I just took a 4e and I evaluated it in all 5 terms of that expression. When I did that, I got this 3,324.692692, and Achieve just wanted us to have a answer to 3 decimal place accuracies, so I maintained well, you can tell 6 decimal places within the problem there. Now, for the lower limit, I just said, well, of course, we're going to subtract it. Then I plugged a 6 into this function with those 5 terms, and I got the 292.2862571. Subtracted that out, multiplied that answer by pi over 4. I got my 2,381.646, and you can see that that was the answer that Achieve needed for this problem. Now, keep in mind, whenever you're doing problems like this with your calculator, it's probably easiest, and you can see how I entered it in here, it's probably easiest if you will work it in like this right here. Notice what I have done, for that lower limit, I stored 6 in for x, and then I just typed my function in just like I had it. And this is where that bottom answer of the 292 came from when I plugged 6 into it. That's where that answer comes from. So I would use your calculator heavily on these problems where it's asking you to do the decimal answers, and then it's no trouble at all. All right, guys, hopefully this helps out with this extremely short section. Let me know if you have any troubles.